Welcome to example number 12. This question, we are going to be looking at finding the average power of someone who's running up a set of stairs. It's a very common lab to do, sometimes in physics class, to find out who's the most powerful person in the class. We could always do this as a quick little lab in class, where we just simply have people run up the stairs and see who is the most powerful. Can you think of what factors affect the person's power? What do you think makes one person more powerful than the other? Does it have anything to do with how quickly they run up the stairs? Does it have anything to do with their mass? Okay, let's dive into this problem. So we have a marathon runner who decides to run up a set of stairs to the top of the Willis Tower, the tallest building in Chicago. The height of the building is 443 meters, and this marathon runner does it in 15 minutes. We are asked to find her average power output in watts and kilowatts and also horsepower. Okay, so let's start off by writing our given down. We know the mass of her. Her mass is 50 kilograms. We also know that she runs it the set of stairs, or all the way up to the top, in 15 minutes. So delta T is 15 minutes. And we also know the height that she's running up. We'll simply call that, you can call that H or delta Y. We're going to use 443 meters. And in this question, we're trying to find, in part A, the power, right? So capital P. And then question B is asking, if the runner's output were collected and sold at a rate of 10 cents per kilowatt hour, what would be the cash value? So I guess we'll just simply call this the cash. Okay, so let's go off to our problem here. So if you recall, power is the rate of doing work or the rate of energy transfer. So if you look at the situation, if you consider this is the system here, the marathon runner, and you think about what kind of energy transformations are occurring, she's got chemical energy in her body, which she's converting into what kind of energy? Hopefully you're thinking, if you consider her and the earth, that would be what kind of energy? It's not kinetic energy as it was in the earlier problem. We are going to assume, by the way, that her velocity as she runs up the stairs is remaining constant. So really she's not gaining any kinetic energy. But she is gaining another form of energy. She's going up a vertical height. Hopefully you're thinking gravitational potential energy. So to calculate her power, we need to find the change in gravitational potential energy. And the change in gravitational potential energy is given by mgh, or delta y. Do we know her mass? Yep. Do we know what g is? Yes, g, assuming she's on Earth, 9.8 newtons per kilogram, or meters per second square. Do we know her delta y? Yep, that's 443, and we know her time. So yes, we can go ahead now and calculate the power. So the power would be the mass of the runner, 50 kilograms. G is 9.8 newtons per kilogram. Delta y would be 443 meters. And then we're running that in a distance of, or should I say not distance, so actually we want time. Oh, another little unit problem right here, right? This is in minutes. Remember, power is in joules per second. So we need to convert that 15 minutes into seconds. So 15 minutes, we're going to need to convert that into seconds. How many seconds are there in a minute? 60, right? 60 seconds in 1 minute. Minutes go on the bottom, so they cancel out. And we end up with 900 seconds, which we now can plug in over here. And then we just need to calculate it now. So the power of our marathon runner is approximately, to 3 sig figs, 241. And if you look at this, let's take a look at those units here. You have kilograms canceling out with kilograms here. You have Newton meters all over seconds. And remember, Newton meters is really joules. So it's really 241 joules per second. Or you could say 241 watts. Or if you convert that to kilowatts, remember there are 1,000 watts per kilowatt. So this is really 0.241 kilowatts. Or if you really want to know what it is in horsepower, then it would be 241 watts multiplied by 1 horsepower over 746 watts. which gives you an answer of 0.323 horsepower. Okay, so now we are looking at part B, and we would like to know if you were to somehow collect the energy that she was performing, and say you were to sell it off as electrical energy, maybe whatever way you could think of, and we want to calculate how much what would be the cash value of her work done. Okay, so you can see, one thing I could say is the rate that she's paying, so that the rate is going to be 10 cents, so that's basically $0.1, and that's per, so I divide, right? Kilowatt, whoops, well that was annoying. Anyway, $0.1 or 10 cents per kilowatt hour. So kilowatt multiplied by hour. Now, you might be wondering, what is a kilowatt hour? Maybe I've discussed in class, maybe I haven't. What it would be a kilowatt hour? We need to convert that. There's a couple of ways. Let's first just examine what that is. A kilowatt is a unit of power, right? Remember, we just calculated kilowatts here. That's power. And then hours is a unit of time, delta T. If you look back at your definition over here, right, you get power is equal to the change in energy over time. If you cross multiply, power multiplied by time is change in energy. So really what they're telling you is the amount of energy. Just a fancy way of saying this is actually energy. You know, why would we put this in kilowatt hours? Well, because your electrical companies sell your power this way. Now, a kilowatt hour, if you were to calculate it, just do this on the side here. A kilowatt hour is really 1,000 watts times hour, right? Remember, 1,000 watts is equal to 1 kilowatt. And 1,000 watts is like 1,000 joules per second. And then you're multiplied by an hour. An hour is 3,600 seconds. So really 1 kilowatt hour is equivalent to 3,600,000 joules. Right? The seconds cancel out here, right? So that's a lot of energy. And your electrical company doesn't actually say, oh, by the way, this is how many joules of energy you use this month. It would be a very large value. So rather than quoting it this way, they write it in kilowatt hours. But really, every kilowatt hour that you use in your household, it represents 3.6 million joules. Okay, and so typically, prices are quoted, 10 cents, 15 cents, 20 cents, depending on where you live, per kilowatt hour when you sell electricity. Okay, back to our problem. So let's say we were to use this energy that she had, right? And we would like to find out how much money she would get. So really what we want to do is we want to find out how much money you would get from this is we need to then multiply by how much energy she has transferred into gravitational energy during this 15 minutes. So going back to our definition, the change in energy is equal to the power multiplied by the time, right? So if we could find out this amount of energy, and I think it would be most convenient to put it in kilowatt hours. Or I mean, I guess you could put in the joules and do some conversions, but let's just try to put this power into kilowatt hours. So really, we want this energy to be in power, and the power to be in kilowatts. And we already did that. That's over here, 0.241. So that's 0.241 kilowatts. And then we want the time, which is 15 minutes, we want that to be in hours. So 15 minutes. And in 1 hour, you have 60 minutes. And really, you have like a quarter, right? A quarter of an hour multiplied by 0.241. So that really gives you an energy of, well, a quarter of 0.241 is 0.0603 and this would be in kilowatt hours. So now, if you want to know the total amount of cash that you're going to get, you would simply take the rate that you have, which is 10 cents or $0.1 per kilowatt hour, and then multiply by the kilowatt hours that she produced in this marathon runner going up the tallest building in Chicago, which is 0.0603 kilowatt hours. And you can see the kilowatt hours will cancel out, and we'll end up with just dollars. So that gives you an answer of $0.00603, or probably better to write it in cents. So that's 0.603 cents. And that's it for this example number 12.